I'm going to be spending most of the time talking about what I've spent most of my time so far on, and that's actually modeling the urban area itself. Sadly, I don't have a ton of this interesting supercell runs to show, but I do have some preliminary results from that. So some motivation for this, these are graphs of population in urban areas, both over the past 60 years and the next 20 to 30 years or so. And as you can see, all over all different countries and all over the world, the percentage of population living in urban areas is increasing, and it's going to continue to increase. And so as people move into urban areas, understanding how urban areas actually affect our environment and the weather will become more important. We know that severe weather can have a pretty significant impact on human lives. This is giant hail that destroyed the side of a house. This is from the Joplin tornado several years ago in Joplin, Missouri. That's one of the hospitals that it hit. So we know that weather can have a big impact on large urban areas when lots of people are concentrated in small areas. The impact of significant weather on those areas on people increases. But we also know that urban areas can affect the weather. You might have heard about the urban heat island effect. Essentially, you replace vegetation with human created surfaces. You decrease the amount of evapotranspiration, so the amount of water that plants give off. You change the properties of the materials on the surface. And you also decrease the amount of water that can actually get into the soil. So this all usually ends up resulting in urban areas being hotter than their surroundings, especially at night. Usually the larger the urban area, the bigger this effect. As you see up here, 3 to 10 degrees C, 10 degrees C would be pretty extreme. 3 degrees C is probably close to average for a decent city at night. You can also have effects where when these obstructions are in the way, wind speed over urban areas can slow down by 30 to 50%, especially as the wind speeds get higher. So it's both a thermodynamic and a kinematic effect with the urban heat island and the slower wind speeds. This is a map. This is just another map to show what happens. This is New York City. On the left is temperature in degrees C, and on the right is vegetation percent. So you can see the darker colors on the left are cool, and the more brown colors on the right are more vegetation. And you can see a direct correlation where you have less urban areas or less vegetation, you have hotter urban surfaces, and the opposite is true as well. This is actually a really recent image. The little crosshairs, the colored crosshairs, are lightning. Lightning strikes. The different colors are just at different times. This is over Louisiana, and if you're familiar with Louisiana, where cities are in Louisiana, that's Baton Rouge, where that cluster of lightning strikes are. That's Lafayette, and that's New Orleans. So you can actually see there's the convection, or the storms and the lightning are concentrated over urban areas. And this has actually been widely studied that especially in tropical environments, pop-up thunderstorms, so thunderstorms that just only last for about an hour, actually have a maximum over cities. So this is actually a really recent example of that happening in Louisiana just about a week ago. So people can try to mitigate the effects of storms on themselves. And at a personal level, this is a giant outer airbag for a car to protect against hail. If anybody saw some of the pictures that came out of Wiley, Texas about a month ago, there was softball hail that destroyed cars. It went through roofs and into the floors of homes. So people do all kinds of things, crazy things. I saw people putting couches over their cars to protect their cars after that event happened when there's some severe weather like a week later. So people will do whatever they can. Safe rooms, another way that people try and protect themselves from tornadoes. This is a storm room in a house that was mostly destroyed. I've seen homes where the entire foundation is gone, or everything's gone, but the foundation in one closet. So people do whatever they can to protect themselves from urban area or from severe weather. But the question becomes, what if we, as opposed to on a personal level, so safe rooms or giant car airbags, what if we could understand more about how urban areas modify the supercell? What if we could find some sort of ideal city shape or size or urban density that you could actually essentially try and modify the storm as it approaches to make it decrease in intensity so that we could do it on a larger scale as opposed to an individual scale. That's just another reason for all of this. Seen a lot. I live in central Oklahoma, just south of Moore, which has been struck by an EF4 and EF5 3 times in the past 15 years. So I've seen a lot of this. And the whole goal is to try and see if we can modify the storms to maybe mitigate some of this. So these are some of my broad research questions. We're going to focus on these top 3. How does the urban area affect the pre-storm environment? So we talked about the urban heat island or the slower wind speeds, and how does the model reproduce those effects? Do those effects and then change the storm? Does it actually do something? And then how might the city's location relative to the storm change it? So if the storm goes south of the city, if it goes north of the city, if it goes right through the city, if it's a storm that hasn't strengthened yet, if it's a mature storm, if it's a dying storm, what do all of these changes and its interaction with the city affect what happens? So the first part I'm going to talk about is actually modeling the urban area without the storm, because we have to if we want to get the effects of the city on the storm right, you have to get the city right to begin with. So for this, I use the weather research and forecasting model. It's very commonly used in meteorology. It's one of probably the most widely used weather prediction model. It's used both in real-time applications. So the Weather Service runs versions of it, and they actually use it to make forecasts. It can also be used in an after-the-fact mode where you can really dig deep into what was going on with different storms and what caused it. It's community, so like I said, it's already developed code, easily scaled for large problems and large systems. All that code is written so that as you choose more processors, it scales itself. Just some things about the science: fully compressible, non-hydrostatic. So there's not too many assumptions made about the atmosphere when we make these, except for these parameterizations. Because the scales go from, you have to consider wavelength scales of radiation and friction and small scale turbulence down at the surface, all the way up to clouds that are on the order of tens of kilometers, hundreds of kilometers. So we have to decide what to parameterize and what to actually predict. So we parameterize short and long wave radiation, surface and subsurface heat and moisture flux based on vegetation, soil properties. That's one of the big things that we're going to be talking about, is the surface of the urban surface and how it's parameterized, and then how that feeds back into what the model is actually seeing. We parameterize turbulence in the atmospheric boundary layer. I forgot the word layer. Usually the scales that we run the grids on are not small enough to actually produce the turbulence that you see in the boundary layer. So we have to parameterize that. And cloud microphysical processes. So you can't predict each raindrop and each snowflake and each piece of hail. So they're usually bulk properties where we might parameterize mass or size ratios. So all of those things have to be parameterized, and your choice of parameterizations can change your results dramatically, especially your atmospheric boundary layer parameterization with severe weather. It makes a huge difference, as does your microphysical properties. It can really drastically change what your results are. Like I said, we'll be focusing on probably not the short and long wave radiation so much as the surface parameterizations. So how does the WRF parameterize urban areas? You have two options. On the left is the NOAA land surface model. It's very simple. There's only about 10 or 12 parameters that they use, and that's used for both urban areas and anything else, forest, lakes, prairies. That's used to parameterize everything in the model, and you can also use it to parameterize urban areas. But there's also the option of an urban canopy model, which only runs over urban grid points. And it takes much more complicated, you can have reflection of radiation off buildings. It takes into account the different materials that they use for roofs, roads, walls. But it is based on, you'll see in this image, essentially it's an urban canyon. So they assume it's something along the lines of what you'd see in like a large downtown area where you have large buildings and basically little canyons in between all the buildings, and that's what they base their geometry off of. So my runs, one of my runs uses the NOAA land surface model, and two that I'm going to show use the urban canopy model, and we're going to see what the difference is. And the big point was trying to figure out which one I use, which one reproduces observations the best. So the model's set up. There's a lot on here. It's 3 nested domains. So the outer domain takes information from a large-scale numerical weather prediction model, and both its initial conditions and its boundary conditions every 30 minutes. We run the outer domain, and then that provides the boundary conditions and the initial conditions for the inner domain, and then that goes down to the third domain. The outer 2 domains were trivial to run. I didn't change any of I didn't run the urban canyon or urban canopy model for any of those. But for the inner domain, it's 500 meter grid spacing, 120 vertical levels, and a 2-second time step. And it was run for 7 days. So that's a lot of time steps, 2 seconds for a whole 7 days. But the idea was to see how well it does on average. If you do it for just 1 day, you might get 1 picture. But if you run it over 5 or 6 days and then average over each day, you get more of a picture of how well it does in general as opposed to one particular day. So the simulations, like I said, I only ran domain 1 and domain 2 once, and then domain 3 is what I started to play with. On the right-hand side in the top, you see land use. The purple colors on the upper left plot are Oklahoma City. So this is over central Oklahoma. And the upper right one is my control run. I basically wiped out the city to see what it provides. If you could go back to 1700 and run this model, what might have happened if the urban area wasn't there, and it helps you look to see, okay, what is the urban area actually doing versus what is the just the topography in general and the vegetation in general doing. And then down on the bottom are urban fraction values. So it's the fraction of each grid point that's considered to be urban, and it helps to determine how it distributes surface fluxes for the urban versus the vegetative. And you'll see, if you look at Oklahoma City there, I don't know how easy the colors are to see. The colors are different, but they match up exactly. So where you see the brightest, the white in the top left, you should see dark red, and it's those exact same locations. And in this case, for this run, the model takes your, what it sees as the vegetation type, or the urban type, and it assigns it a value. It doesn't take any real information into account other than what the land use type is. But on the bottom right, you'll see in general lower, cooler colors, so lower urban fractions. That's actually derived from observations, where they actually look at what percentage, I believe it's 30 meter grid spacing observations over the whole United States. So that's much more accurate of what your urban fractions actually are in the urban area. So the bottom left is going to be what I'm going to call SLUCM1, Single Layer Urban Canopy Model 1, where I let the WRF decide what the urban fraction values are and run from there. And then on the bottom right, I override that and I say, no, you use these urban fractions. And that's going to be what I call SLUCM2. And the whole idea is to look and see how well the land surface model without the urban canopy models runs compared to the two down at the bottom, the two urban canopy model runs. just some quick information of some of the computational aspect of it. Each DO3 run was a little over 300,000 time steps, greater than 19 million grid points. And about each time step was between 1.28 and 1.44 seconds. The urban canopy model adds on another layer. It adds on another call that it has to do, so that adds about 0.15 or so seconds. But over a lot of time steps, that actually adds up to a couple of hours in computational time. So if I could, I would prefer not to run the urban canopy model, just to cut down on some times, especially with the supercell runs. When you start adding on microphysics, it really takes up a lot of time. Microphysics is really computationally expensive. So some of the results, I apologize for what happened to my image when I brought it over to this computer. But these are averages of over all urban grid points minus averages of rural grid points in the surrounding areas. It starts from 0 UTC and goes to 0 UTC, and they're average over 5 days. If you can see the gray shading on the left side of each panel, that's nighttime. So that's sunset to sunrise. So it gives you an idea, even though you can't see the exact times, of approximately when this occurs relative to the solar cycle. So in the black, you'll see observations. There was a dense network of about 30 observing stations in Oklahoma City. In the real world at the time that I ran this simulation, so we can compare those. Oklahoma also has a mesonet where we have at least one observing station in every county. So it provides a relatively dense network of rural observations as well. And so that's what the black line is. The red line is the SLUCM1, so that's where you have the denser city. And then the blue line is the land surface model, so the one without the urban canopy model. And then the yellow line is the lower density urban area. So some things to point out. Luckily I labeled with bigger letters so you can see that the top row is actually computed first model level. So that's what the atmosphere in the model is actually seeing. And it's what really matters. The bottom row, because we make our observations at like 2 meters and 10 meters, if you see a stick, they try and parameterize them down to those heights for comparison, but they're really sensitive to surface fluxes, and the model isn't actually saying those. Those are just to compare to observations. So I much prefer to look at the top row because that's what's actually getting ingested into the rest of the model and what would actually matter. So you'll see here, that's temperature. All 3 runs are too cool. So where you see positive values above the dark black line, that would be the urban area is warmer than the rural area, which is what we would expect, especially at night. So the black line is above all of the model lines most of the night, with the red line, the SLUCM1, being warmer than the other 2. So it's closer to observations, but its urban fractions are actually less realistic than what's going on in the other 2. So that's a problem when you provide it with more realistic surface representation, and it gives you, or more realistic surface representation, and it gives you a less accurate representation of what the atmosphere is seeing. So that's a problem. This is mixing ratio, so it's a measure of how much moisture is in the atmosphere. As you can see in the observations at night, that's like a 25% difference in the humidity in the urban area as opposed to the rural areas, and the model doesn't do that at all. None of them seem to do that well. So that to me says it's not a problem with the urban parameterization. It's something else going on. It may be the boundary layer and surface layer parameterization. It's something I'm not sure what's going on. But the biggest problem is the wind speeds. Wind speeds, as you see with the black line, should be lower all throughout the day in the urban area. Lots of observations have shown this. And the blue line, you can almost not see the blue line because it follows the observations really well. So the land surface model is reproducing these lower wind speeds in the urban area really well. And the urban canopy models are pretty much out to lunch. I'm not really sure what's going on. They don't look anything like it. And if I were to put a supercell in here, a storm, it would interact with the city at about the time those wind speeds were low. really low. And so it's really important. That's a 30% difference in the wind speed, which for surface vorticity could make a really big difference. So basically what this tells me is I'm using the land surface model. The temperatures might not be quite as high as I would like them to be, but the wind speeds are really important to get right. So in the next few runs that I'm going to show you, they do use the land surface model. So now we'll look at the Supercell runs. I only have a few to show you. It's the same basic domain setup, same parameterizations. This is a May 31st case. If anybody's familiar, there was the largest tornado ever observed on this day. It's 3 miles wide. It was giant in central Oklahoma that day. The only thing I changed was I made the smallest domain a little bigger to fit more iterations of the city in. Oh gosh, you can't even see. So essentially the goal would be to have a 9 by 12 matrix of city locations all over the domain, and to compare the location of the city to the storm and what happens to the storm strength and evolution as it gets near the city. So the performance for these is, it takes a lot more time, but a large part of that is because there's a lot more microphysics going on. When you put Supercell in there, every grid point that has the storm in it has to run microphysics. And that's really, it takes up, like I said, it's at the beginning of the run, it starts out about 1.3 seconds per time step, and towards the end, it's over 2 seconds. So it makes a really big difference. And the bigger domain obviously makes a much bigger difference. So some eye candy. This is essentially what simulation of simulated reflectivity looks like. And you'll see where those black lines are on the animation. That's updraft helicity. That's essentially a measure of how fast the storm is rotating and how strong the storm is. And then on the right-hand side, those are 11 runs, all starting from east to west. They're right in the center, and then they slowly, as you move up from the bottom thing on the legend upwards, they move further north. And this is essentially the kinds of analysis I'm going to be looking at these to see, and moving it east and west and seeing if the interaction of the city with the supercell changes as the supercell matures and then dies towards the end of the simulation. You can actually see some peaks in here relative to what most of the runs are doing. So the idea would be to look for those peaks or look for valleys in some of these diagnostics to see if we can find a pattern with these to see what's going on with the supercell in the urban area. So what's next? I'm going to continue to do more of those city runs to end up having about 108 with the Dallas-Fort Worth area and lots of different locations to see what the change is. Try different cities. Oklahoma City, mostly plain states, because that's essentially the kinds of cities you usually see with supercells anyways. Try idealized shapes to see if there's, if round versus star-shaped versus a square-shaped city makes a difference. And then a factor separation. We talked about how the urban effect on the atmospheres it's twofold, at least for what I'm looking at, and to see which one makes a bigger difference. Is it the heat of the city? Is it the wind speed of the city? Because usually when I give this presentation to a group of meteorologists, I always get the question, which one is it? Because people want to know. And hopefully I can answer that question, at least for the simulation. As for the real world, I don't know, but the simulation hopefully will give us something to go off of.